Okay, if we're going to create a line based on this table of values, the only point we know is right here at 0, 3. I guess the only question we have here right now is, do we want the line to go up or do we want the line to go down, and by how much? Let's say I want my line to go up, and let's say I want it to go up from 3 at when x is 2. Let's say y is 7. And then, so it's gone up by 4 every time x goes up by 2. So if x goes up by 2 more again, we should go up by 4 more. And if we go up by 2 more again on x, we should go up by 4 more on y. Now if I go back in my table, so if I go back 2, I should go back 4, which brings me down to -1. And if I go back 4 more, I'm down to -5. Now notice we did create a line, and when you check yours, you can have any line you want as long as you check every time this goes up 2, this y goes up by the exact same amount. Okay, now we're going to use this example to talk about partial variation, which is different than direct variation. Notice that the lines here, when connected, do not pass through the origin. They pass through some other point. In this case, they pass at 3 on the y-axis. So they do not vary directly to each other. Notice that there is no constant multiple from 2 to 7 or 4 to 11 and 6 to 15. There's no number to multiply 6 by to get 15, and that same number to multiply 4 by to get 11. These are not directly related, these two variables. So we say that these are partially related. So if I'm going to, we're going to talk about this example, one of our main characteristics is that this line does not pass through the origin. And notice that's that part here, and that's any time you have a linear equation not passing through the origin, we have a partial variation linear relation. Notice in the table, when the independent variable is 0, this is a number, and that also is our indicator from the table of values why they're not partial, or why they are partially variated. So the last other part of our kind of how to recognize partial variation problems is from the equation. And all equations, since they're not directly related, there's this like offset. There's this number that kind of puts it off. So they're partially related to each other. So the equation looks like this. It starts the same way. We've got y equals, and then we've got m, which is our constant of variation, times x. And that constant of variation is very similar because these are related by going up by the same number. Okay, so we've got y equals mx, but we have to kind of offset it. So we have this plus this kind of b, which is our starting value. Okay, so our m is the same. It's still our constant of variation. But the b this time, since that number is there, we call this kind of our fixed value or our initial value. All right. So to continue, let's find out our equation for our line, or my line that I've drawn. Notice that the constant variation is always what, every time the independent variable changes by 1, what does the y variable change by? Notice that as the independent variable changes by 2, our y variable changes by 4. So if every time this goes up 2, this goes up 4, every time x goes up 1, y must go up by 2. So our m in our case is 2. And that's because we're taking that 4, the change in y, divided by that change in x. And that's how we got that 2. So our constant variation is 2. And the initial value, or our fixed value, is the starting value, which is also always the y-intercept. So our y-intercept is 3. So here is our equation. Y equals that constant of variation, 2, times the independent variable, plus that fixed value, 3. That's our equation. It's got that m and x, and it's got that initial value. Notice there's like 2 parts to the equation instead of our direct variation equation, which is 1 part.